If you spin a simple coil of wire inside a magnetic field, boom, you get electricity. It sounds almost too simple, right? But that is the fundamental principle that powers our entire world, from these massive power plants all the way down to the device you're watching this on right now. So today, we're going to explore the two fascinating and kind of opposite effects of this one single action.
So, let's kick things off with a question. When you spin a piece of metal inside a magnetic field, are you creating the incredible power needed for a whole city? Or are you creating the massive braking force you need to stop a high-speed train? Well, the amazing answer is you're doing both. It all just depends on how you spin it.
And this incredible duality is exactly what we're breaking down. On one hand, you've got the AC generator, which is all about harnessing rotation to create useful power. And then on the other hand, you have let's call it its unruly twin, eddy currents, where that very same rotation creates a powerful opposing force. It's like two sides of the very same electromagnetic coin.
Okay, so let's dive into the first half of our story, the AC generator. This is where we get to see Faraday's law of induction in its most practical and, honestly, its most powerful form. The whole principle is just beautifully simple. First, you take a coil of wire and you just spin it inside a magnetic field. Now, as it's spinning, the amount of that magnetic field that's actually passing through the coil, that's what we call magnetic flux, is constantly changing. And according to Faraday's law, anytime you have a changing magnetic flux, you induce a voltage, or an EMF. Simple as that. To really get a feel for this changing flux idea, let's use an analogy. I want you to picture that spinning coil like it's a window spinning in a heavy downpour. When the window is flat, facing the rain, it's going to catch the absolute maximum number of raindrops, right? But as it turns and becomes edge-on, it catches, well, zero. The magnetic flux going through that coil changes in exactly the same way as it rotates.
And this relationship gives us this really elegant equation. See, the flux at any given time depends on the cosine of the angle. Faraday's law says the EMF is the rate of change of that flux. So when you do the math, when you take the derivative, that cosine flips to a sine. And that's what gives us this beautiful sine wave pattern for the voltage. The instantaneous voltage, which we call epsilon of t, climbs up to a peak, we call that epsilon naught. And that peak value just depends on the number of turns in the coil, its area, the strength of the magnet, and of course, how fast you spin it. All right, let's put this to the test. This is a classic question from the CBSE exams, Q5, and it asks a really simple question. When does the polarity, the positive or negative direction of that induced voltage actually flip? And the answer is every half revolution. It's that simple. For the first half of the spin, the voltage is positive, and then for the entire second half, it flips and becomes negative. That changeover point happens right at the 180-degree mark. Just think about that sine wave. As the coil spins from 0 degrees all the way to 180 degrees, the wave is up in its positive phase. But as soon as it crosses that 180-degree mark and keeps going to 360, it dips down into its negative phase. That exact crossing point is where the polarity flips. Now here is a super common trap for students. Pay attention to this. To get that nice alternating AC output, we use two continuous slip rings. They let the coil spin around freely and just transfer that alternating voltage right out. But if you were to use a split ring commutator instead, you'd actually be building a DC generator. That's because the split ring is designed to cleverly reverse the connection every half turn, which keeps the output current always flowing in the same direction.
Okay, so we've seen what happens when you spin a nice, neat coil of wire. But what if you just take a solid chunk of metal and spin that in the same magnetic field?
Well, this is where we meet our unruly twin, eddy currents. These are basically circular loops of current that get induced inside bulk conductors, we're talking solid pieces of metal, anytime they're in a changing magnetic flux. It's the exact same principle as the generator, but instead of the current flowing nicely in a wire, it just swirls around inside the metal itself.
A really great way to visualize this is to think of eddies, or whirlpools in water. In our generator, the current flowed in a very defined channel, right? The wire coil. With eddy currents, it's as if little whirlpools of current are forming all over inside the bulk material. They don't have a specific path, so they just swirl.
And these little whirlpools can be a huge problem. In things like transformers and motors, they generate a ton of heat. And this is just wasted energy. We call it I²R loss. It tanks the efficiency and can even cause parts to overheat and just completely fail.
So, obviously, engineers needed to figure out a way to tame these unruly whirlpools. And the solution they came up with, it's actually incredibly clever.
So instead of using a solid metal core, they use what's called a laminated core. See, a solid core is like a giant, low-resistance playground for huge eddy currents to form, and that generates tons of heat. But a laminated core breaks up all those paths. It dramatically increases the resistance and shrinks the currents down, which means way, way less heat loss.
And the process is actually pretty straightforward. You take your metal core and you slice it into these really thin sheets. Then you coat each one with an insulating varnish. Finally, you just stack them all back together. The real key here is that the insulation stops the current from flowing easily between the sheets.
Think about it this way. If you try to stir a big whirlpool in a solid disk of pizza dough, it's pretty easy, right? But what happens if you cut that dough into individual slices? Well, a big whirlpool can't form anymore. It's all broken up. Lamination does the exact same thing to eddy currents.
So, we've seen how to create power, and we've seen how to tame that wasteful side effect. But what if we could actually use that opposing force? This is where we get to harness the full, awesome duality of induction.
It turns out that undesirable braking force is incredibly useful for things like electromagnetic brakes on trains and roller coasters. It is a super smooth, powerful, and contactless way to slow down. We also use the intense heat from eddy currents in induction furnaces to melt metal, and their ability to mess with magnetic fields is the whole principle behind metal detectors.
So, let's just pull this all together. With an AC generator, the goal is to generate power, plain and simple. We force rotation to get a current. With eddy currents, the goal is usually to oppose motion. The induced current itself creates that opposing force. One gives us our power plants, the other gives us electromagnetic brakes.
And that kind of leaves us with a final thought. We've seen how one single law of physics, Faraday's law of induction, can be used to both create immense power and create a powerful braking force just by changing the shape of the metal. It really makes you wonder, what other amazing things can this one fundamental principle do?